So we're entering chapter 14 in the Nelson chemistry textbook. We're making a big switch. We're jumping into electrochemical cells. We're going to apply our knowledge to two types of cells within Chemistry 30. For both types of cells, we're going to go through over the next 3, 4, 5 lessons. These definitions are always going to apply. So the anode is the electrode where oxidation occurs. You can think of that if everybody's looked at a battery, there's a negative end and there's a positive end. So that's what I kind of mean by electrodes. Okay? The end where we get oxidation is what we refer to as the anode. Now it has to be a solid piece of metal that we can literally put a wire to. The cathode is the other end. It's the end that has reduction. Now we'll talk about polarity as we go through our lessons, positive and negative. Is the anode plus or minus? But it's always where oxidation occurs. Cathode is always where reduction occurs. Not a new definition, but I need to make sure you're comfortable with anion. We're going to use that terminology. You're going to have to tell me where anions move in solution, and you're going to have to tell me where cations move in solution. When we build an electrochemical cell, and we're going to start off with voltaic cells, we're going to have all of the OA reactants and their products in one beaker. We're going to have all the RA reactants and their products in another beaker, and we've got to connect them. One of the pieces of the connection is going to be a salt bridge, an aqueous solution that's hot, that has ions in it that connects one half cell to another. Okay? The completion of the loop will be an electrical wire that runs from the anode to the cathode, or cathode to anode, a wire that goes across the two electrodes. And that's how we get our loop. Wire from one electrode to the other through our solution, through the salt bridge, and then back to the other electrode gives us our loop. Okay? We're doing some physics here. Okay? We need our salt bridge to contain a conductive solution that has ions in it, and we call conductive solutions electrolytes. So that's why you need to be familiar with that term. So cathode and anode are the two main new ones. Okay. So we're going to talk about this voltaic cell. I had electrochemical cell as the heading. That applies to the whole unit. Now we're talking about one of the two specific types, voltaic. You're going to draw this cell nice and big, and then I'm going to label what is going on using our knowledge of losing electrons, gaining electrons. Where do the electrons flow? Where do the ions flow? Where are chemicals being used up? And where are products being formed? So I want to understand the chemistry before I can start tackling where's the electrons flowing, where are the ions flowing. In standard voltaic cells, you have both sides of the half reaction for both chemicals. And when you have both sides of the half reaction, you'll find that whatever half reaction is higher up in your table will always have the strongest OA at it, and the lower down beaker with the other half reaction will have the best RA, because the OA is always highest in the table and RA is lowest. And we're going to have both sides of the half reactions. We have copper metal and we have copper ions. That's both sides of one of our half reactions. We have zinc metal and we have zinc ions. That's both sides of another half reaction. We just have to find those two. The highest will be at the OA, the bottom will be our RA. So there's our copper half reaction, and we've both sides. Much lower in our table, we have our zinc half reaction. Okay. The higher up half reaction, what's on the left, will be our best oxidizing agent. The lower down on the right, that chemical will be our best reducing agent. And that's going to tell us our chemistry. So I'm going to summarize that chemistry. You don't have to do the 5 steps to predict. You just have to find your two half reactions. Okay? The highest one up will have our best oxidizing agent. OAs are on the left. So copper 2 plus aqueous will gain 2 electrons and make elemental copper. The best reducing agent comes from the lower down half reaction, and RAs are on the right. This is the one we flip. So the zinc is going to react, the elemental zinc is going to make more zinc 2 plus ions, and it's going to lose 2 electrons. Now I labeled OAs and RAs, that's kind of how I think of our table, but the anode and cathode come from oxidation and reduction. That's our definition on the previous slide. So I'm going to add in a different color, our oxidation reduction. So our best oxidizing agent is going to be our reduction, our GER, our gaining electrons. We got electrons at the beginning. Our RA, that whole equation will be our oxidation. That's our losing electrons. And if you mess this up, if you think Leo and GER, you should be able to correct yourself if you improperly identify. So this copper beaker that has the ions as our OA, that's going to contain one of our electrodes. Now the copper is reduction, so we can flip back. Reduction is going to be where we have the piece of metal that is our cathode. That's just one of the many definitions you need to get comfortable with. So where's our piece of metal? There's our piece of metal coming out of our voltaic cell, and this one would be our cathode. The oxidation is occurring on the other side. The piece of metal that you can connect a wire to is your electrode, and that's going to be our anode. So I'm going to start doing a bunch of labeling now to your nice large diagram. I'm going to talk about electron flow. Okay. You have to think of where are electrons coming from. Let's go down to our chemistry. What is spitting out electrons? Is it the cathode spitting them out or the anode? Let's add another letter. We got our OA, we got reduction, that's going to be our cathode. We got our RA, we got oxidation, that's going to be our anode. Okay. You can rock this unit, but you got to keep all these definitions straight. This is a vocabulary heavy unit. So which electrode is spitting out our electrons? That would be at the anode where there's oxidation. Oxidation produces electrons. So electrons, it's going to be the actual zinc metal in our electrode is going to react. They're going to release electrons, and the electrons will take the path of least resistance to the other side, and a nice conductive wire is the path of least resistance. So from our anode, electrons are going to flow to the cathode. They're lost at the anode, they're gained at the cathode. Now at the cathode, they're going to go through the wire, down through the cathode, down to the solution so they can be gained by the copper 2 plus ions, down in solution. The anode is where electrons are coming from. Electrons are negative, so your anode is your negative terminal. Okay. So you should not put your tongue on any terminal of a battery, but particularly the anode, because that's where electrons are coming from. Then you put your tongue on the cathode, the electrons could be ripped out of you, which is still bad. But the negative terminal of the battery is where the electrons come from. The cathode is where they go to, and that's the positive terminal of a battery or a voltaic cell. Because the voltaic cells are really a form of battery. They're a very rigid definition of a battery, a special type of battery. Okay. That has to have both sides of a half reaction. So we've done a fair bit of labeling. We've got all these electrons going from the anode to the cathode, which would cause the cathode, that blue copper side, to be getting negative and more negative and more negative. And that's not going to be sustainable. You can't keep building up negative charges on one side, the left side in this case. So we need something to balance out the negative charges. So we need positive charges to balance out the negatives going this way. So from anywhere in solution, and particularly the salt bridge, cations will move towards the cathode to balance out that electrical charge that's going that way. If 1 mole of negative charge goes to the cathode, 1 mole of positive charge of ions will move. Now, anything that's positive in either beaker is going to head towards the cathode, not just from the salt bridge. The opposite is going to happen at the anode. We're losing negative charges as electrons leave, so we need negative charges in the salt bridge or anywhere in solution to move towards the anode. We have nitrate spectator ions down in our solutions. Okay, we have nitrate in our salt bridge. All of those negative nitrates from anywhere in our solutions will be moving. Okay. You must label ion movement in solutions. You must label electron movement through the wire. Okay. Now, you can draw these with the cathode on the left or the cathode on the right. Both are correct. You can't memorize the electrons always go from the right-hand side to the left-hand side, because you can flip the diagram around. Okay. You need to know they go from anode to cathode. Okay. So that's the key pieces to analyzing a voltaic cell, and you'll definitely be asked on quizzes or assessments to be able to draw and label the movement in voltaic cells. Let's end this slide by putting in the changes in the chemicals. And our reactions are going to guide us. What's going on at the cathode? Well, copper 2 ions are reacting away. They're gaining 2 electrons and becoming elemental copper. So our copper 2 plus ions, okay, will end up migrating towards the cathode, picking up 2 electrons, and making more elemental copper. This electrode is going to get bigger. Elemental metals will want to stick to elemental metals. Ionic compounds don't do this. You make sodium chloride salt, it doesn't stick to a metal per se. But if you make more copper metal, elemental metal, which is brown, just like a penny, you would see the mass of brown going up and up and up the longer we build this cell or run this cell. Okay. The ions are blue. Copper 2 is a nice blue, and they're going away. So you would see the blue color fade away as the cell runs. Now that I can't really draw on the diagram, the fading of a color, so I'm not going to label that. So blue fades away, the electrode gets heavier, gains copper mass. The opposite is true at the anode. The zinc elemental metal, which is the electrode, is going to react away. So this electrode is going to lose mass. That I can't draw, so I'm going to label. It's a reactant. And we're going to get more zinc 2 plus ions in solution. Their concentration is going to increase. You know, they don't have a color, so we won't see that. But you could potentially weigh the electrode before, weigh it after, and see that mass difference. Okay. Now, every half reaction is unique, so you can't memorize the cathode always gains mass, the anode always loses it. That's not true. Some half reactions have no solids in them at all. Your H plus to hydrogen gas, it's the 0 line on your table, has no solids in that half reaction. So there'd be no change in mass of either electrode when that half reaction is used in either direction. So you have to use the chemistry to figure out whether an electrode is going to get heavier, lighter, or not do anything. So a very intense slide. We're trying to condense, we're trying to be simpler. Cell notation is our theme. And cell notation is going to be just this black box, or the structure of the black box. Now, everything around that black box are the trends and patterns to cell notation. cell notation, you must start with the anode first, which is negative, and that's a solid. You put a vertical line, and then you tell the reader what electrolyte, or if you've gaseous, you would include those after the first dash. The double dash, double vertical line, is when you're switching from one half cell to the next. You're switching beakers. Then you list the electrolyte that's in the beaker with the cathode. So the aqueous solution, or if there were gaseous, you put that. A vertical line, and then you put the solid cathode, which would be your positive electrode. So we've got a lot of the other pieces summarized. The electron flow is always from anode to cathode. That's not written into cell notation, but you need to realize the electron flow is always from what's written first, the metal that's first, all the way to the metal that's at the end. You always have the oxidation first. So the oxidation is going to occur before that double line, and oxidation, that half reaction will have the Ra reactant at it. The reduction, the GR that occurs at the cathode, will have the reactant that's the strongest oxidizing agent. And they can be a pairing, same as we saw before. The cation movement is always towards the cathode. The anion movement is always towards the anode. To remember these, I just remember consonant to consonant. Cations move to cathode. Anions move towards the anode. That's how I keep it straight. I sort of never forget the C to C and the A to A. So let's write the cell notation for the previous slide. I'm going to put in the lines first. And we've got the format at the very top. We must start with the anode first. Now, our anode is on the right-hand side of your diagram. That was the zinc. The copper was at the cathode. Okay? So you can't just look at the ordering of your diagram. What solid did we have in the anode beaker? The right-hand beaker, that was the elemental zinc. Okay? So we have to have a solid we can connect a wire to. It happens to be a reactant. Then we put anything we have in solution. Now there's two conventions that you can follow or that you might see. You might see just the chemicals in the half reaction, or you might see the spectator ions included. I'm going to drop the spectator ion out of this cell notation. So it was zinc nitrate. Okay? You could see the nitrate written in. I'm going to leave it out. Either is acceptable. We're going to move over our double line where we're into the cathode side, the cathode beaker. We have to put the aqueous solution first. So that was the copper 2+, the copper nitrate. I'm going to leave the nitrate out because it wasn't part of any of our half reactions. Then we need the solid, the actual cathode, and that's the copper metal. Now the cathode was not one of our reactants. Cathodes and anodes don't have to be reactants. They just have to be the physical metals. So everything looks really good. We can draw our cells. We can do cell notation. We're going to keep addressing issues. What we're going to address next is the fact that a lot of your half reactions have no solids in them whatsoever. So how are we going to deal with a reaction like that 0 voltage one in the middle of your table that is hydrogen H+ turning into hydrogen gas? Now that's going to get solved by using an inert electrode. If you have no solids at all in your half reaction, you're going to have to use one of these. It's an electrode that provides the electrical connection, the solid that we can put a wire to, because we need a metal aqueous interface for the chemistry to occur at. but it's inert. It's not an OA, it's not an RA, it's not gaining or losing electrons, it's just a conductive medium. A very common, cheap inert electrode is a graphite rod, which is solid carbon. Another more expensive option is platinum, solid. You need to be able to recognize both of these on tests or diplomas as inert electrodes. They're not part of the chemistry. You can make an inert electrode really easily if you have a pencil. If you sharpen both ends of a pencil and you stick it in a beaker, that's a graphite rod. Okay. The bottom end of the pencil is where you get electrical connection with the solution, and you connect your wire to the top sharpened end of the pencil. Okay. There's lots of YouTube examples of pencils being used as electrodes. You stick a sharpened pencil, you stick it into a lemon, you're on your way to potentially making a battery out of a lemon. Okay. Most of the time they stick two different metals in, not an inert electrode. So what is this going to look like? You've got the theory, but in practice, okay, it would look something like this. Okay, I'm just going to do the cathode side. Maybe you have that hydrogen half cell occurring at the cathode. So the hydrogen half cell, that 0 voltage in your reduction table, has hydrogen ions. Okay. It's got hydrogen gas. I'm going to include both of those, both the gas and the aqueous part, before I do the single line. But then there's no solid inherent to the half reaction, so you would either see pure carbon or pure platinum written in. I'll pick pure platinum. So that would be the electrical connection into where the aqueous solution and gas is located, but you're going to ignore it in terms of OAs, RAs predicting your chemistry. You will do labs where you have to use inert electrodes. So let's use our skills to solve a problem. So write the equations for the half reactions. So we have two half reactions to write, and the overall reaction occurring in the following cell. So we've got cell notation to go backwards from, and then we have to do a label diagram. So cell notation, if you understand it, can really make our life quite easy. Lets us solve these faster. You could always do the 5 steps, write everything that's present, find the best OA, find the best RA. That works, but it's a waste of time when you have cell notation. If we think of our sides, there's conventions. We have to have certain agents and certain sides. So I'm going to start on the right-hand side. I want you to think, what's on the right? You could always flip back in your notes. Do we have the OA and the cathode, or the RA and the anode on that side? This is the best OA at the cathode side. So I'm not even going to look at iron 2 or iron 3 trying to find the best OA. I'm just going to look, so my OA at the cathode, I'm just going to look at dichromate and H+. And there's a reason why both of those are listed. Okay? Now I see carbon in inert electrode, so I know that's not part of the OA. So I look on the OA side of my table, I kind of start at the top, and I find dichromate and H+ fairly quickly. So I'm focusing in on selective chemicals to find the best OA. So I'm going to grab that half reaction, Cr2O7 2- aqueous, we have that, plus 14H+, aqueous, we have that. So we have both pieces to that oxidizing agent. And then we need 6 electrons, and we can make 2 chromium 3+ ions and 7 water. Okay. want to kind of do the opposite, the best reducing agent, which is going to occur at react at our anode side. The metal anode is going to come from the left-hand side. And we have another inert electrode. So we're not going to look for elemental carbon. We have iron 2 and iron 3. So we're scanning the Ra side of our table at the bottom, working our way up till we hit one of those two. And the only one you hit is iron 2 as the reducing agent. So the iron 2,3 half reaction is going to occur at the anode. We've got the dichromate one higher up that's going to occur at the cathode, our best OA. So we've got Fe2 plus going backwards compared to what's in our table. Fe2 plus is going to turn into Fe3 plus. And it's an oxidation. It's going to lose an electron. So that's our two half reactions. We can get our net, find the lowest common multiple of electrons. We got 6 and 1, so that's going to be 6. So I have to 6 times the green half reaction. 1 times 6, 1 times 6, 1 times 6. Okay. So the electrons in blue that are gained are the exact same electrons in green that are lost. I can write out the net and then go right into our diagram. So dichromate plus 14H plus aqueous plus 6 Fe2 plus. Two chromium 3 plus, 7 water, and 6 iron 3 plus ions. The order that you write the chemicals doesn't matter. Now, your chemistry teachers in this department love to ask about colors. The diploma started to really ask about colors. So watch a question that says, tell me some observations in this voltaic cell. Page 11 on your table tells you about colors. Iron 2 is there, iron 3 is there, chromium 2 is there, chromium 3 is there. So you should be able to tell me what colors are fading away and what colors are being formed. You should also be able to use your acid-base knowledge to tell me something about pH. Okay. We have an acid reactant, so you're going to use up H+. So as you use up H+, you're going to get less acidic. So the pH would actually increase towards 7 over time. So if you ever wonder, why do we do so many labs? Why do you have to write all these diagrams? I've been counting diplomas over the last 7 or 8 years and how many questions are lab-based, and it's often maybe 25 to 30% have some connection to a lab and lab skills. So draw a diagram, and then you need to practice this. So I'm going to get started with the generic pieces. We're going to need 2 beakers. We're going to need a salt bridge. Okay. We're going to need some salt in that salt bridge. You've already seen sodium nitrate. Sodium chloride will work fairly well for most labs. Sodium ions and chloride ions are not good OAs or RAs. We're going to need electrodes in each of our beakers. Okay. I haven't even looked at the question yet. I'm just drawing the pieces that are always present. We're going to need a wire to complete our loop. Now this wire is referred to as the external cell. The internal cell is the metals, the elemental metals, the aqueous solutions. Okay. The external cell is the wire. Okay. Now I've kind of got to look at my chemistry to keep labeling. Okay. Now I have a choice. I could put the cathode on the left or I could put the cathode on the right. It doesn't matter. So there's two possible drawings for this. Okay. I'm going to choose to put the anode on the left. Okay. So I had to pick that. So I'm going to label that side as the anode. I kind of had free choice over that. That makes this side negative. Okay. And what is that anode? The anode is an inert iron 2 and 3 is reacting there, and it's an inert electrode carbon. So I labeled the type of electrode and exactly what material it is. What's in this solution? It's the Fe2 plus and the Fe3 plus. I do not have room to write aqueous in my diagram. On the other side, I'll do the solutions first. We've got dichromate, Cr2O72 minus. Again, I won't write the aqueous for the sake of space. And we got H plus. When you label the chemicals, you don't have to put a count in. You don't have to go 14H plus. The diagram will just have what chemical. So this is going to be our cathode, which has a positive polarity, and it is a second inert electrode, a carbon electrode. From our cell notation tells us that. So let's label some movement, and then I'll check that list and see if I've covered all the required parts. Electron flow, that has to be anode where we have oxidation. So our anode is losing electrons, and the electrons are going to go towards the cathode. We're going to have ion movement, and I remember vowel to vowel and consonant to consonant. So let's see, vowel to vowel. Anions go to the anode. So that would be chloride ions are negatives. There are anions, and they're going to move towards the anode, as well as any spectator ions. So that might be iron 2 nitrate. That nitrate's negative. It'd be moving also. Cations to cathode, so our sodium plus ions are going to be moving towards our cathode. And anything positive in solution is going to move towards our cathode. We're not going to get any solids whatsoever. There are no solids in our half reaction, so both electrodes are going to stay the same mass. You take them out, you dry them off, you weigh them dry before, you weigh them dry after, then you don't change. Okay. Let's see what I've labeled. Draw a cell, including labeling electrodes, I did that. The electrolytes were the dichromate, the H plus, the iron 2, the iron 3, the direction of electron flow, and the direction of ion movement. I've answered all the pieces, so I don't have to do any more. Okay. Again, you should not be shocked to get questions about pH, colors, electrodes getting heavier. Okay. So that was an intro to voltaic cells. You got a lot, so I summarized everything on one slide. Okay. I'll put that one on D2L. I don't have it as my next slide. But you need to practice now before we move into standard cell potential. So I'm not going to do this, but this is what's coming next, the math, the voltage. Okay.